In this video, we are going to start a new series, Inference for Variable Parameters. I want to begin by talking about Z-based confidence intervals. In order to talk about Z-based confidence intervals, we should review what a Z-score is. Z-scores are also called Z-values, standard scores, or normal scores. They go by various names. I'm going to use the name Z-score. A Z-score is a transformation of a score to the deviation from the mean in standard deviation units. Here's the formula. In the numerator of this fraction, we see deviation from the mean. The score is represented by y. The population mean is represented by mu. So this is a look at how far the score is from the population mean. If we divide that by the standard deviation to put the deviation from the mean in standard deviation units, we have a Z-score. When Z-scores are normally distributed, they form a standard normal distribution. That's because in the standard normal distribution, a value of 1 on the score axis represents one standard deviation, so it is the same as one Z-score. We use the standard normal to calculate Z-scores that will serve as our critical values when we're going to create a confidence interval. The Z-score that we choose depends upon the level of confidence that we want. For example, here are some symbols indicating critical values that put 95% of the area between these values. That means we want a confidence interval in which we can have 95% confidence that the population mean is going to be captured within the interval. In order to find these critical values, we need to see how much area is beneath each one. So for example, if you look at the upper critical value, that has 97.5% of the area beneath it, or in proportions, 0.975. So I'm symbolizing here that we need a Z with 0.975 of the area beneath it in order to get that upper critical value. Similarly, for the lower critical value, we need a Z with 2.5% or 0.025 of the area beneath it. Now typically what we do is we only take the upper critical value. That's because these critical values are symmetrical. The Z 0.025 is the same as the Z of 0.975 if we look at the absolute value. That is, if we look at it without the sign. So the Z of 0.025 is simply the negative version of the Z with 0.975. We can find Z-scores for means just like we can find Z-scores for regular scores. Here's the formula again for a Z-score. Suppose the score is actually a mean. That would be the case if we had a sampling distribution of means. In that case, we can replace the score by the mean in the formula. Now I have y bar, and I'm looking at the deviation of y bar from the population mean. I divide this by the standard deviation of the mean. So whatever score we're using on the top in the numerator, whether it's a y or a y bar, we need the standard deviation of that in the denominator. Putting this all together, we can create a confidence interval for the mean. Here again is the Z formula based upon finding a Z-score for the mean. If we do a little bit of algebraic manipulation, we get something that looks like this. Notice that if I multiply both sides of that top equation by the standard deviation, I have Z times the standard deviation. We see that appearing in the confidence interval, and we call that the margin of error. I add and subtract that margin of error from y bar in order to get an interval around the mean. Now actually what I'm doing is I'm taking two z's. For a 95% interval, that would be the z at 0.025 and the z at 0.975, and then adding them to y bar. However, if we think of it as just taking the z for 0.975, that is the upper critical value, then you can get the same result by simply subtracting and adding the margin of error from y bar. The population mean, mu, will then fit within this interval, and we are 95% sure that this will happen because 95% of the intervals we construct will in fact include the population mean. So let's look at an example. Suppose that after 64 students went through the GRE test prep course, that they took the GRE and the average of their GRE scores was 153. Now we know that for the general population, the average of GRE scores is 150. So we're interested in knowing, what about if everyone took this test prep course? Would that average come up? That is, would the population mean be higher than 150? And exactly what would it be? That's the question we're asking here. Let's use R in order to find this answer. I'm going to start by setting variables for the things I know. I know that the sample size is 64, so I'm going to set n to be 64. I know that the mean of the sample, not the population mean, we don't know that. The mean of the sample is 153, so I'm going to set y bar to be 153. I know enough about the GRE to know that the standard deviation of the GRE is 8.75. So I'm going to set the standard deviation, SD, of GRE to be 8.75. Those are the things we know, and with this, we can calculate a confidence interval. First, we need the standard deviation of the sampling distribution of means. That is, we need the standard deviation of means. That's the original standard deviation divided by the square root of n. So I'm taking the original standard deviation and dividing by the square root of 64. When we look at the standard deviation of the sampling distribution, we see that it's about 1.1, much smaller than the standard deviation of original scores. That was 8.75. Now suppose I want a 95% confidence interval. That means I need to find a z-score that has 0.975 of the total area, where the area is represented by 1, beneath that critical value. That's a z that I can find using Q-norm of 0.975. Notice that I don't need to tell Q-norm the mean and standard deviation of the normal distribution because I'm using a standard normal distribution, and that's what R is going to anticipate as the default if I don't put in a mean and standard deviation. So I'm going to find that z-score. It's about 1.96. Now if I take these two values and multiply them, the product of the z-score that serves as our critical value and the standard deviation of the means is equal to the margin of error, which I've symbolized here as μ. Now all I need to do is subtract μ from y bar and add μ to y bar in order to get my lower bound and my upper bound for the interval. My lower bound is 150.9. My upper bound is 155.1. So the confidence interval is between 150.9 and 155.1. Let's go ahead and see that written out in symbolic form. Here it is. We are 95% confident of the mean for all students who enroll in this GRE preparation program, and that will be somewhere between 150.9 and 155.1. Notice that the test prep may not be helping very much, because one possible mean is a mean of 151, only 1 point above what students earn on average when they do not do test preparation. It could, however, be as high as 155. Now, we would have to make a decision based upon the cost of the program whether an average gain of 5 points is meaningful or not. That's a non-statistical decision, but as statisticians, we've provided the information needed in order to make that decision.